Here's the efficient solution. The trick is that we're going to use recursion, and I'm not going to show you something called the trellis diagram, which is a way of thinking about a graph model of this, but what we're going to take advantage of, remember the Markovian property? The Markovian property says that the probability of going to some state only depends upon where I am now. It does not depend upon how I got here, right? So if today is sunny, the probability of tomorrow being sunny is not affected by whether yesterday was rainy, snowy, or sunny. That's my assumption. It's my first order Markovian assumption. So to take advantage of that, we're going to define some auxiliary variables and define a recursive algorithm. So the first thing we're going to define is what's called the forward variable alpha. Okay? And alpha sub t of I is defined to be the probability of seeing all the observations up until time t, and at time t being in state I. Okay, that's exactly what it says in this, well, now there's a box inside the box there. So it's the probability of seeing everything from 1 until t and being in time t being in state I. The really cool thing about that is I can define a recursive definition for this very easily, all right? So you start off, A1 of I is what? Well, it's the probability of having seen the observation at time 1 and the probability of being in state I at time 1. Okay, well that's easy. Pi sub I is the probability of starting in state I, and Bi of O1 is the probability of seeing that first symbol if you were in state I. So that's how you initialize it. Now comes the really cool thing. And before we write it out, think about it this way. At some time t, the probability of landing in state j is going to be, well, either I was in state 1 before and I ended up at state j, or I was in 2 before, or I was in 3 before, or I was in 4 before, right? And these are what are referred to as mutually exclusive, so the probability is just the sum of them. And that's how this is written here, right? What this says is that alpha of t plus 1 of j, so that's the probability at time t plus 1 of being in state j and having seen all the 1 to t plus 1 observations, is just, well, just as I said before, it's the sum over all the different possible states, right? There's n possible states of possibly being in those states at time t, that's what alpha t is, right? And alpha t also includes all of the observations up through t, times the transition probability of going from I to j. Remember, we're trying to compute alpha t plus 1 of j, going from I to j. So that's the probability that I land in the state j. And now I also have to talk about the output symbol at time t plus 1. Well, that's b sub j of ot plus 1. All right, and there's no way of thinking that I can reach that j state from any of the preceding states, so I just define that recursively. That means I can do one more really cool thing, okay? So I could obviously run this all the way to t. So I could tell you the probability of seeing all of the observations, 1 through cap t, and landing in state 1, and all the observations and landing in state 2, and landing is... Suppose all I want is the probability of the observations, right? I don't actually care what state I end up in. Well, that means that the probability of the observation given the machine, and that's what we're trying to compute, is just the sum of all the alpha cap t of i's, right? Alpha cap t is the probability of seeing all of the sequence of I, meaning and landing in state I. I sum that up over all the i's, and that's the probability of the entire observation sequence. So you recursively solve that problem. So remember before it was n to the t, which is a really, really awful number. The complexity of this is just n squared t, okay, through the recursion. Each time step you have n squared things you have to look at, you do it t times, and so it's n squared t. And for any reasonable numbers, n squared t is way, 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 way less than n to the t. All right. So that's that efficient solution of the using the forward algorithm, and allows us to solve that first problem.